This is problem set 39, the last problem set of the course, where we're going to be talking about Gibbs free energy, some applications thereof, and doing a lot of math with Gibbs free energy. So problem set 38 was a lot of conceptual stuff with Gibbs free energy, and problem set 39 is a lot of the math. So let's just take a quick second and review how we calculate Gibbs free energy. So if we want to calculate the delta G of a reaction, the delta G naught of a reaction, meaning at standard conditions, 25 degrees Celsius and 1 atmosphere, then we can do so by taking N times the delta G naught of formation of the products minus N times the delta G naught formation of reactants. Okay, because the values tabulated in the book for delta G's of formation are at standard conditions, then doing this math will give us delta G of the reaction at standard conditions. Now let's say that we don't want standard conditions. Let's say that we want to figure out the delta G at a different temperature. Well, then we can just use delta G equals delta H minus T delta S. And you can think of these as being delta H naught and delta S naught, meaning we can find delta H naught by doing delta H of formation products minus reactants. Products minus reactants. Find delta S naught as products minus reactants using H and S values from the book. And then we can get delta G, but we can pick the temperature we want to get it at. And the other idea to remember is that delta G is greater than 0 for spontaneous. Sorry, for non-spontaneous. Delta G is equal to 0 at equilibrium. And delta G is less than 0 for a spontaneous process. And that should get us through most of the problem set. So let's keep going. One thing to be aware of, you'll want Appendix 4 open, or you'll just be Googling a lot of delta G of formation values. And I've just got all the values written down already, so I won't be jumping between the book or anything. But use delta G naught formation values in Appendix 4 of your book to calculate delta G for this reaction, for the combustion of diamond, and determine whether it's spontaneous under standard conditions. Okay, so we're using delta G naughts, we want standard conditions, so we're just going to do products minus reactants. So when I look it up, the delta G values here are 2.84 kilojoules per mole. Delta G's of formation, similar to delta H's of formation, are 0 for elements in their standard state. So you might wonder, well, why isn't carbon 0? This is carbon, this is diamond. In the standard state, carbon is graphite. So even though it just says carbon, we know it's diamond, so it's not in its standard state. And then CO2 is negative 394.4 kilojoules per mole. So the delta G of this reaction is going to be products minus reactants. We've got negative 394.4 kilojoules per mole. Products minus reactants is 2.85 kilojoules per mole plus 0. The oxygen. And when we do that, we get delta G for this reaction. I should say delta G naught for this reaction. This is negative 397.25 kilojoules per mole of reaction. All right, so that's easy enough. Use thermodynamic values in Appendix 4 of your book to calculate delta G for the reaction. Notice it's not delta G naught. Delta G for the reaction for the combustion of diamond at the temperature of 5,000 degrees Celsius. Determine whether it is spontaneous at that temperature. Oh, so we've got to say here, is this spontaneous or not? Delta G is negative, so it must be spontaneous. So basically, diamond will burn, is what that tells us. Determine whether it's spontaneous at 5,000 degrees. Okay, well, we cannot use delta G values from the book and do products minus reactants because those are for standard conditions. This is at 5,000 degrees Celsius. So we're going to have to use delta G equals delta H minus T delta S. Which means we need delta H of formation values from the book and S values from the book. So I'm not going to do this every time, but let me just write out a little chart of carbon, O2, CO2, delta H of formation, and S. Okay, so we know that delta H of formation for a pure element is in its standard state, is going to be 0. S, however, is not. Remember, S is 0 for a pure element in its standard, or for a pure crystal at 0 Kelvin. All right, so I'm going to just write these down. This is negative 393.5 kilojoules per mole. This is 213.6 joules per mole Kelvin. CO2 is 1.88 kilojoules per mole. I should have said C, not CO2. And this is 2.43 joules per mole Kelvin. And 0 kilojoules per mole. And 205 joules per mole Kelvin. Okay, so I've got to find delta H and delta S, and then I can plug in my 5,000 degrees. So delta H of the reaction is going to be my products. So negative 393.5 minus my reactants, 1.88, and my oxygen is 0. And then delta S of the reaction, same thing, 213.6, 2.43 plus 205. Gives me a delta H of reaction of negative 395.4 kilojoules per mole, and a delta S of reaction of 6.17 joules per mole. Okay. All right, so now we can plug this in. So we'll have delta G equals, but before we do this, if we want to plug these in, we need both in joules or both in kilojoules. So let's put them both in kilojoules. So this would be 6170 kilojoules per mole Kelvin. So delta H is going to be 395.4 kilojoules per mole minus T is 5273 Kelvin times delta S, which is 6170. Oh, I did that backwards, didn't I? I did. That's not true. Let's change them to kilojoules. This becomes 0.00617. There we go. 0.00617. I get delta G for this reaction. Let's see. And I get that delta G for this reaction let's see what I do wrong. Negative, oh, there we go. Negative, that's what I missed. This is negative, so that's negative. Negative 395.4. There we go. Delta G is negative 428 kilojoules per mole. And therefore at high temperatures, diamond still burns, which we would kind of expect. Your intuition would say that if diamond burns at normal temperatures, then it would burn at high temperatures too. All right, use the delta G naught formation values in Appendix 4 to calculate delta G for this reaction, determine whether it's spontaneous. So same thing as 1A. So let's get our values, and we're going to end up doing a similar thing here. So why don't I just write, I'm going to write all of the values. So we're going to have our delta H of formation, delta S, nope, just S, and delta G's of formation. Okay, so CO2 PbO PbCO3. And here delta, this is negative 393.5. And this is 213.6. Again, these are just values from the back of the book. I'd imagine these would be in the back of the book. If not, just Google them. Oh, kilojoules per mole. And 68.7 joules per mole K. PbCO3. Okay, so in the first one, we're trying to find its standard conditions, so we're just going to do products minus reactants. And the reaction's already balanced, so we just use products are CO2 and PbO. Minus my reactants is negative 625. That gives me delta G of this reaction is positive 43.2 kilojoules per mole. Because it's positive, that tells me this is non-spontaneous at normal conditions. Okay, but then I'll just move this down so we can do the next part of the problem, which wants us to test it at 325 degrees Celsius. So we're going to have to use delta G equals delta H minus T delta S, so we can pick our temperature. So then our delta H, so a little bit. Delta H for our reaction going to be products minus my reactants, and same thing for delta S of the reaction. Get 88.3 kilojoules per mole for the delta H of the reaction, and the delta S of the reaction get 151.3, and I'm just going to change that to kilojoules. So I know in my delta G equation I'm going to have them in the same units. Alright, so now I can say delta G of the reaction is going to be 88.3 kilojoules per mole minus temperature, so 325 plus 273 gives me 598 Kelvin, and delta S is 0.1513 kilojoules per mole K. And I get a value, delta G for my reaction at 325 degrees Celsius will be negative 2.18 kilojoules per mole. And therefore, at that high temperature, this reaction is spontaneous. whereas at the low temperature of 25 degrees Celsius, it wasn't. My mistake, sorry. Okay, tungsten is the favored metal for light bulb filaments, in part because of its high melting point. The enthalpy and entropy of fusion for tungsten, so we have our enthalpy of fusion and our entropy of fusion, so I can write that here. Delta H of fusion, delta S of fusion, respectively. What is a melting point? Okay, so we're dealing with a temperature change here. And you could solve this based on stuff that we talked about in entropy. And let me kind of explain it in a different way here. So we're trying to find the temperature at which tungsten will begin to melt. So you're imagining at low temperatures, tungsten's not going to melt. As you increase the temperature, it's not going to melt, not going to melt, not going to melt. And then at some temperature, and above that temperature, it's now spontaneous for tungsten to melt. So that means that at some temperature, we make the transition from positive delta G to negative delta G. Well, at the temperature of that transition, the point at which the switch between non-spontaneous and spontaneous happens, delta G is going to be 0. Okay. The result of that is that I can rearrange this equation. I get T delta S equals delta H, and I can divide by T and get delta S equals delta H over T. This may look familiar when we talked about entropy. We said if you have a phase change, you can just find the entropy as the total heat or total change in enthalpy over T. Okay, and that's because at a phase change, at that exact temperature, you're at equilibrium, and so delta G is 0. Okay. In this case, though, we're solving for temperature, so I could rearrange the equation differently and say its temperature is going to be delta H over delta S. And so my temperature, my delta H of fusion is 35.4. I'm going to change it. Now we need these in the same units, right? So I'm going to change this guy to joules. So I get 35,400 joules per mole divided by 9.58 joules per mole K. And that gives me the temperature of fusion, or the melting point of tungsten, is going to be 3695 Kelvin. And there we go. Okay, problem 4. Use thermodynamic values in Appendix 4 of your book to predict the temperature at which hydrogen peroxide boils. Okay, so very similar to here, we want to find the temperature at which something becomes spontaneous. In order to do that, we know delta G is going to be 0, so we need delta H and delta S for that process, and then we can find the temperature at which something becomes spontaneous. So I'm just going to write that here. We know that 0 equals delta H minus T delta S, and so the temperature is just going to be delta H over delta S. Okay, so we got to look up these values for H of formation and S, and so H2O2, let's see how I have these written. So H2O2 is going to be negative 136.1 kilojoules per mole and 232.9 kilojoules per mole, except I think that's H2O2 as a gas, and H2O2 as a liquid is negative 187.8 kilojoules per mole. These units are wrong, and 109.6, but these are joules per mole K. Right, so the delta H of my reaction here, and my reaction is this phase change. It's going to be products, negative 131.6, no, negative 136.1, minus my reactants. And then the delta S naught of the reaction is going to be 232.9 minus 109.6. That gives me 51.7 kilojoules per mole. There for the delta H of the reaction, delta S of the reaction is going to be 123.3 joules per mole K, which is 0.11233 kilojoules per mole K. Right, so now I can just jump over here and say the temperature at which this becomes spontaneous, the temperature at which delta G equals 0 is going to be 51.7 kilojoules per mole divided by 0.1233 kilojoules per mole Kelvin. Which gives me a temperature. Did it ask for units? Nope. So then I just get my final temperature as 419 Kelvin. Awesome. Now we're going to use thermodynamic values in Appendix 4 to predict the temperature at which methanol boils. So methanol boiling is going to be CH3OH liquid going to CH3OH gas. So if I look up the delta H of formation and the S values for each of those, this is negative 201.2 kilojoules per mole, and this is negative 238.6 kilojoules per mole. There we have 237.6 joules per mole K, and here we have 126.8. So the delta H of my reaction, or really I could say the delta H of what is it doing? It's vaporizing, so vaporization. Product minus reactant. And the S naught, or the delta S naught of vaporization is going to be 237.6 minus 126.8. That gives me 37.4 kilojoules per mole for the delta H of vaporization. And the delta S of vaporization, I get 110.8. And I'll change that to kilojoules. So then the temperature at which it becomes spontaneous to boil is going to be delta H over delta S. And I get a temperature of 337.5 Kelvin. There you go. So using the delta G equals delta H minus 2 delta S equation, we're able to identify the temperature at which something switches from spontaneous to non-spontaneous, or from non-spontaneous to spontaneous. All right, one source of sulfuric acid aerosols in the atmosphere, which make acid rain, is the combustion of high sulfur fuels such as coal, which releases SO2 gas. That then is further oxidized into SO3 in the air, according to that equation. The SO3 then combines with water, forming fine droplets of sulfuric acid in the atmosphere, according to that equation. Use the appropriate delta G formation data in Appendix 4 to calculate delta G naught. So we're just going to do products minus reactants for both reactions and determine if they are spontaneous under standard conditions. Okay, so I'm going to write here the delta G not formation values for each of these guys. So SO3 is negative 371.1. I'll just say all of them are in kilojoules per mole. SO2 is negative 300.1, and O2 is 0. So I had forgotten to get the values for H2O and sulfuric acid, so I just went and grabbed those, and there we go. So we're trying to find the delta G, not a formation, for each reaction. So for this first one, delta G not a formation is going to be products minus reactants. 2 sulfuric acids. My products minus my reactants is 2 SO2s. Sorry, I shouldn't have said sulfuric acid. 2 SO3s here, and then 2 SO2s. And 1 oxygen. And that gives me a value of negative 142 kilojoules per mole. And then this second one, delta G not of formation, of reaction. Products minus reactants. And I get negative 81.67. Reaction 1, reaction 2. Because both values are negative, both reactions are spontaneous at the 25 degrees Celsius where we got these values. Right? So at 25 degrees Celsius. Okay, number 6. The breakdown of glucose in the cells begins with a process called glycolysis. Glycolysis is the main source of energy during anaerobic metabolism, a form of metabolism in which inhaled O2 does not play a role. Glycolysis occurs in a series of steps. One of the steps involves the conversion of fructose 6-phosphate to fructose 1,6-diphosphate. The reaction is shown below, along with the change in Gibbs free energy at standard conditions. So here's a reaction. Don't worry about what those molecules are, but basically what this is saying, this should be a not a crosshairs. The delta G of this reaction is positive. So, is this reaction spontaneous under standard conditions? Nope. Delta G is greater than 0. But we know this reaction happens in the body. So let's explain how coupling this reaction to another reaction can make the process spontaneous. So let's talk about what coupled reactions are. Basically, our body does this all the time. If you have one reaction that has a positive delta G and therefore is not spontaneous, okay, so let's say one reaction delta G1 is 5 kilojoules per mole. So this is not going to happen. But what I can do is I can take that reaction, our body does this all the time, we can take that reaction and run that reaction in the exact same place at the exact same time as another reaction that has a negative delta G. So let's say I run reaction 2 and it releases 10 kilojoules per mole of free energy, which can then be absorbed by reaction 1 to make it happen. That's called coupling reactions, putting a very spontaneous reaction with a non-spontaneous reaction so that both happen together. Okay, so we could combine this with a reaction whose delta G is less than or equal to less than negative 17 kilojoules, because then together they're guaranteed to be negative. That's called coupling reactions. Right, what sign of delta G would be necessary to make the overall process spontaneous? So the two reactions together, so like in this case, the two reactions together have a delta G of negative 5 kilojoules per mole. So in this case, same idea. What sign of delta G would be necessary to make the overall process spontaneous? Together, you'd have to have a negative sign of delta G. Write an inequality to determine the minimum or maximum value of delta G for the coupled reaction to make the overall process spontaneous. Okay, we kind of talked about that. But we know that delta G1 plus delta G2 have to be less than 0. And the reaction they give us has a positive 17 kilojoules plus delta G2 has to be less than 0, which means delta G2 has to be less than negative 17 kilojoules when I subtract it over to the other side. With the hydrolysis of ATP, according to this reaction, with a delta G naught of negative 31 kilojoules, be sufficient to drive the conversion of fructose 6-phosphate to fructose diphosphate. Spin why or not? Absolutely, yes, because positive 17 plus negative 31, those are my two reactions. That gives me a value of negative 14 if I know how to do math. Yep, and that is negative, so it's going to be spontaneous. So we can make those, the one thing we do want, work as long as we combine it with ATP, which releases a lot of free energy, and that's what our body does. All right, coupling of reactions can be used to make non-spontaneous reactions occur. For example, in glycolysis, some of the steps produce ATP rather than consume it. Okay, basically what that's saying is our body uses ATP, which means that must be spontaneous, but it also produces ATP, which means there must be some way to make that spontaneous. Given the formation of ATP from ADP, according to this process, with a positive delta G of 31 kilojoules, that's not spontaneous. Answer the following questions. What must be the sign and magnitude for any reaction that is coupled to this reaction to make it spontaneous? Write an inequality. Well, if delta G of this one is 31, then we're going to have to get one with a delta G that's less than negative 31 in order to get the combined delta G to be negative and therefore spontaneous. Could the conversion of this phosphoenol pyruvate to pyruvate with a delta G of negative 62 kilojoules per mole be coupled with ADP? Absolutely, right? Yes, because positive 31 kilojoules plus negative 62 kilojoules equals negative 31 kilojoules. So that would become spontaneous. Okay, so there's a couple of applications. Oh, that's the end. A couple of applications of Gibbs free energy, because Gibbs free energy is really the driving force that makes reactions happen. And so we can use what we know about enthalpy and entropy to find the temperatures at which stuff becomes spontaneous. And we can use information about Gibbs to figure out if stuff is spontaneous. And we can use Gibbs free energy to understand coupling of reactions.